All right, I think let's just get started. As people roll in, they can catch up or whatever. So welcome back. This week is probably the worst recitation you'll attend of the semester. For me personally, it's my least favorite one to teach because, I don't know, there's just really nothing too exciting about determinants, right? You're just trying to find a number. There's also this problem where like some people have seen this stuff before, so it's just a colossal waste of their time. And then people that haven't seen it, we tend to go through this section really quickly, and then they have to scramble to catch up. But hopefully we can learn something out of it. So what's going to happen today is that I'm going to wrap up inverses really quickly at the beginning. I'm going to spend 40 minutes on determinants, and then the last 5 to 8 minutes, I'm going to try to introduce vector spaces, which will probably just leave you all really confused leaving this class today. But it's okay. You'll get it to lecture. You'll talk about it in lecture tomorrow. And then I'll do announcements at the end. Okay, so let's wrap up inverses. Okay, so I'm going to make sure that I'm actually recording. Yeah, okay. So for those of you that have or don't know, realize that on my website I do have a recording of last week's recitation, which is actually your guys' class. Okay, so wrapping up inverses. So let's go back. An n by n matrix A is invertible if the following is true. And this is the section in your book called Invertible Matrix Theorem. And it's 2.8 or 2.9, I forgot which section it is. It's one of the sections. But essentially what it does is it gives you a bunch of conditions that tell you that a square matrix is invertible. The first one is that rank A is equal to n. All right, so if you have full rank for a square matrix, you have an invertible matrix. The second one is that the system AX equals B has a unique solution. All right, for every B in Rn. So this is for every. Okay, so that means when you have the system AX equals B, right, no matter what B you put in on the right-hand side, there's only going to be one X corresponding to that B. And the way you can see it is if you invert the matrix A, right, if you multiply both sides by A inverse on the left, you'll get X is equal to A inverse times B, and that's going to be like a unique vector. So that's the case. The third one then, the system AX equals 0 has only the trivial solution, X equals 0. So what does that mean? That means that if you do AX equals B, there's only one solution, AX equals 0, there's only one solution to that system, and it's going to be X equal to 0 vector. All right, and if that's true, then your matrix is invertible. And then 4, determinant of A is not equal to 0, and we're going to get to this today in class. Okay, so what does this mean? This essentially means that all these 4 conditions are the same thing. So if you know that one is true, then you know that everything else is also true. Okay, so one of these implies every other condition. And usually what will happen is that if your matrix is invertible, you can use all of these. So this is really useful then for those proof type problems or show that this is true type of problem, where if you have invertible matrix, you might want to consider using one of these 4 conditions. Okay? Any questions? So that's really all I want to talk about with invertible matrices. Everything else you've done in class or we talked about really briefly last recitation. All right, so let's get to determinants then. And in Math 114, you were introduced to determinants in terms of the cross product. Right? So for example, if I have two vectors, 1, 2, 3, cross 4, 5, 6, right? What do you get? Well, you did I hat, j hat, k hat, 1, 2, 3, 4, 5, 6, and you took the determinant of this matrix in a few ways. One way that you did was, right, you crossed out the first row, first column, and then you took the determinant of that, multiplied by I, and then you crossed out the second row, second column, first row, second column. And another method you did was like you did this thing. All right, do those look or sound familiar at all? All right, just one heads up, don't ever do this in 240. Just don't. The reason is because this only works, the diagonal line method, this only works on a 3x3 matrix. So if we give you a 4x4 and you do this, you're just going to get a 0 because it makes no sense. So this method is off the table. But in general, what we did, right, we calculated the determinant. So this is 12 minus 15 times I hat. And then you subtracted, now this is 6 minus 12 times j hat plus 5 minus 8, right? 5 minus 8 times k hat. All right, and so you get this vector -3, 6, -3, or more properly speaking, -3 I hat plus 6 j hat minus 3 k hat. Right? So that was the cross product in 114. The idea is exactly the same in 240. So in 240, what we're going to do is that we're going to calculate the determinant in two methods. The first method is going to be the cofactor expansion method, or I think McGrath calls this the row or the column expansion. Okay, and the idea is the same as Math 114, except there's a little twist to it that we can add. So, for example, if we take this matrix, 5, 0, 4, 0, 3, 0, 2, 0, 1, okay, and notice that these square brackets, right, I'm writing like straight lines rather than like curvy matrix brackets. These straight brackets means I'm taking the determinant of what's inside. Okay, so if I take the determinant of this, we can do it the Math 114 way, where we start off the top, and so this is 5 times the determinant of 3, 0, 0, 1, and then we subtract 0 times the determinant of 0, 0, 2, 1, and then we add 4 times the determinant of 0, 3, 2, 0. Okay? And what do we get? We get 5 times 3 minus 0 plus 4 times the -6. And so we get 15 minus 24, we get -9. All right, so that's the cofactor expansion method. However, there's actually an easier way to do this. All right, and the thing is the following. The 5, the 0, and the 4, right, all came from expanding across the first row, right? So here we had to do essentially two calculations. We had to calculate this determinant and we had to calculate that determinant. I can actually expand along one of the rows or one of the columns here where I only have to do one calculation. All right? And does anyone see what row or what column that would be?
0, 3, 0.
Yeah, so I could expand along the second or the second row or the second column. And in that way, I only need to do one calculation because I have 2 zeros, right? So let's see that in action. So we'll take the same matrix again. 5, 0, 4, 0, 3, 0, 2, 0, 1. Okay? And instead of expanding like this along the top, what I'm going to do is that I'm going to go along a column. All right? So I'm going to take this column, and that's going to be where I expand. So my first calculation is going to be along that 0. And it's going to be 0 times, and now you have to be careful. the 0 is the 1, 2 entry. Right? It's in the first row, second column. So I have to multiply this by -1 raised to the 1 plus 2. Okay? And this is why, when you did the cross product in 114, you had that -j. It's the exact same reason. Right? So it's 0 times -1 to the 1 plus 2. And then now we have to multiply the determinant of whatever's remaining. Okay? So what's remaining is 0, 2, and 0, 1. So we find the determinant of that. Well, we don't actually have to in this case, because the 0 takes care of it. Okay, so that's the first term I calculate. Then I'll calculate 3, all right, times -1 raised to the 2 plus 2, right, because this 3 is in the 2, 2 entry. And then what's remaining is 5, 4, 2, 1. And then lastly, so we expand along 3. Now we need to expand on the 0 on the bottom. So now this is going to be 0 times -1. And this is the 3, 2 entry. So this is raised to the 3 plus 2. And then what's remaining is 5, 4, 0, 0. Okay? So notice that instead of expanding along the top, I've expanded along the middle column. Right? And why would I do that? The idea is, okay, well, this is 0 times something, so I don't even need to calculate this thing. This is 0 times something, so I don't even need to calculate that. Right? And so the only calculation that I need to do is 3 times -1 raised to 2 plus 2 plus determine that. Well, that's 3 times 1 times 5 minus 8, which is going to be 3 times -3. All right. Any questions? So this is my preferred method of finding determinants. What you'll usually see for a determinant question on a midterm is that you're going to get a 4x4 or larger matrix, and you're going to be asked to find the determinant of that, right? And so, generally speaking, you'll have some row with enough zeros to tell you that that's going to be the row or that's going to be the column that you should expand on, all right? And so the idea is the same. You just do, so for a 4x4, you'll just have some value times -1 raised to the whatever, except this matrix will be like a 3x3 matrix that you need to find, right? So I would recommend this method because I just like it more than a row reducing method, which is what we'll talk about next. Okay, so any questions on cofactor expansion? Okay. What's next? So the second method we can use is the row reduction method. Okay, and the row reduction method uses the following fact. Is that the determinant of an upper or lower triangular matrix is the product of the diagonal entries. Okay, so for example, right, if you have 1, 1, 1, so you have the 3x3 identity matrix, well, we just multiply the diagonal, that's equal to 1. If you have like 1, 2, 3, 0, 4, 5, 0, 0, 6, we just take the product of the diagonal, which is equal to 24. And then if you have something like -3, 0, 0, -1, -2, 0, 0, 0, 1, right? Again, this is a lower triangular matrix, but we just take the product of the diagonal, and this is going to be equal to 6. Okay, so we use this fact, Another thing we need to use is that we need to use the thing between row operations and determinant. All right, so there's an interaction between performing row operations and finding determinants, and they're going to be the following. So firstly, if I know that A, B, C, D, E, F, G, H, I is equal to some determinant Q, I can find then a scalar multiple of one of the rows. All right, so let's say I had KA, KB, KC, DEF, GHI. Right, so I scalar multiply. Let's see, how should I write this? Scalar multiply row by K. All right, so if I know that A, B, C, D, F, G, H, I is determinant Q, what should be then the determinant of this resulting matrix with a scalar multiple of K? Yeah, exactly. So it's going to be K times the original determinant, which is Q, right? So I've multiplied one of the rows by K, the entire determinant of the matrix changes by a value of K. All right. The second row operation we can do is the following. So you can take A, B, C, D, E, F, G, H, I. That's equal to some determinant Q. And I'm going to permute, let's say, row 1 and row 3. So now what I'm going to get is I'm going to get G, H, I, D, E, F, A, B, C. Okay? And what's the determinant of this? Yeah, minus Q. Okay, so whenever we switch a row, whenever we switch any two rows, our determinant goes from positive to negative. All right, or just flip signs. Okay, the last determinant that we want to worry about then is the following: A, B, C, D, E, F, G, H, I is equal to Q. And let's say I added, or I replaced row 1 with row 1 plus 2 times row 2. So what do I have now? I have A plus 2D, B plus 2E, C plus 2F, D, E, F, whoops, G, H, I. Okay, and what's the determinant of this resulting matrix? Yeah, it's just Q. Nothing changes. All right, so your three types of elementary row operations, right? This is the only one that leaves the determinant unchanged, is when you add a scalar multiple of one row to another row. Okay. If you multiply by K, if you multiply a row by K, it becomes KQ, and if you permute rows, you flip signs. Okay, any questions? All right, so now that we have this, and we have the fact that the determinant of an upper triangular matrix, or lower triangular matrix, is the product of the diagonal entries, we can use the row reduction method. So, for example, let's take a look at the following determinant: 2, 1, 3, 0, 7, 14, 4, 1, 5. All right, so the goal of the row reduction method is that if we reduce this matrix into a triangular matrix, right, we can just take the determinant of the triangular matrix, and then any like permutation or like scalar multiplication that we had to use in getting to the triangular matrix, we'll just have to take into account what we did there. All right, so what we want to do then is we row reduce this into the an upper triangular matrix like we usually do. So we want to zero out these guys in the first column. So 2, 1, 3, 0, 7, 14. And then I'm going to do row 3 replaced with row 3 minus 2 times row 1. And so that would be 0. 1 minus 2 is negative 1. 5 minus 6 is negative 1. All right. And do I need anything out here to adjust for the row operation I just did? No. All right, next step, we're going to do the following. There's a multiple of 7 in that row, in row 2. So I'm going to take that out. So now it's 7 times 2, 1, 3, 0, 1, 2, 0, negative 1, negative 1. All right. And then lastly, I'm going to add row 2 to row 3. So I'm going to replace row 3 with row 3 plus row 2. So this is going to be 7. Don't drop the scalar out in front. 2, 1, 3, 0, 1, 2, and then 0. Negative 1 plus 1 is 0. Negative 1 plus 2 is 1. Okay. So the determinant is equal to 7 times 2, right, because of the diagonal. And we see that our determinant is 14. Okay, pretty simple. Any questions? All right. So another type of problem that you'll see that's very popular with, or very popular in the determinant type of problems is if you have a matrix of unknowns. So if you're finding the determinant of a matrix of unknowns, which is the following type of problem. You have something like A, B, C, D, E, F, G, H, I, and they'll tell you that this determinant is some number, like 6, right? So now you want to find the determinant of D plus 3G, E plus 3H, F plus 3I, 4G, 4H, 4I, A minus 2D, B minus 2E, C minus 2F. Okay, so you know one thing, and now you have to find the determinant of this other thing. Okay. So, did you guys do an example like this in class at all? No? Okay. So, what happens sometimes is that, and you might have seen this in class, but when you're doing these row operations, there's one row operation that causes a lot of confusion, which is the scalar multiplication one. And the problem is, do I multiply by 1 over k, or do I multiply by k? Right? So a lot of times it's like, do I divide by k, or do I like actually multiply by k? So usually what I like to do is that, so this is like a really simple matrix right here, right? It's like A, B, C, D, F, G, H, I. And then this one is like the more complicated one. So what I like to do is I'll just start with the complicated matrix, and I'll essentially perform row operations, in a sense, backwards to get down to the simpler matrix. So I'm going to rewrite it, all right? And so if you perform row operations starting with the more complicated matrix, you're always going to take the scalar from inside the matrix and you're just going to move it out, all right? So the scalar is what it appears to be. So for example, in this next step, I'm just going to take the 4 out of the middle row, right? And there's no multiplying by 1 over 4. It's just 4 out in front. Everything else, first row stays the same. You got GHI in the middle row, A minus 2D, B minus 2E, C minus 2F. Okay, so I took the 4 out of the middle row. And what's the next step? Well, any ideas? Yeah.
Could the new row 1 just be row 1 minus 3 row 2?
Row 1 minus 3 row 2. Yeah, so that's exactly what we want. So we want to replace row 1 with row 1 minus 3 row 2, and that way we get rid of the GHIs in row 1. And so we're left with D, E, F, GHI, A minus 2D, B minus 2E, C minus 2F. Okay? And the next step, same idea. We want to get rid of these DEFs in the bottom row. So I'm going to do row 3 minus 2 times row 1. And I'm going to get DEF, GHI, ABC. Oh, what did I forget to do? Yeah, I forgot the 4, right? So I even said don't drop your scalar out in front. It happens. All right, so the 4, remember that? Okay, so this almost looks like what we have here, just some row permutations that we have to do. So now we just need to start permuting rows. So if we switch row 1 and row 3, we'll get a negative 4, A, B, C, G, H, I, D, E, F, right? And then lastly, we need to switch again. So we're going to get a negative 4, which is just a positive 4, but A, B, C, D, E, F, G, H, I. Okay, now what's the determinant of this thing? 6, right? It's given up here. So my determinant of this big matrix is going to be equal to negative or positive 4 times 6. So then this determinant is equal to 24. Yeah.
Why is it equal to 6?
I just said it was equal to 6. It's just given to you. So that's why we're trying to get down to A, B, C, D, E, F, G, H, I in the first place, is because we know what that determinant is, but we don't know what this is. So that's why we row reduce down to this guy. Okay, any questions? So the other way they'll do it is they'll give you they'll give you the determinant of this matrix, and then they'll make this guy unknown, right? And it's the same idea, because you just, now this will be determinant, and then this will be like something, and then you just divide both sides by whatever's out in front. Okay, let's see. 6. All right. Yeah.
The last step. Oh wait, never mind. I see the negative.
Yeah, it's negative 4. Sorry. Any other questions? All right. So, all right. Let's talk about the applications then of determinant. So those are the two ways you find determinant. You either row reduce to upper triangular matrix, or you use cofactor expansion. Really, like, they should be free points on the exam, but like silly mistakes happen with determinants. So just whenever you see a determinant problem, just double check your math to make sure you don't take a negative sign when you need a positive sign. Okay, the first big thing that determinants tell us is invertibility. Invertibility. Okay? And it's the following. If I know that the determinant of A is equal to 0, then A inverse doesn't exist. All right? It does not exist if determinant of A is equal to 0. If the determinant of A is if the determinant of A is not equal to 0, then A inverse exists. All right, and I think we mentioned this at the beginning of class with the 4 things. Okay, so determinant A not equal to 0, then A inverse exists, etc. Okay, so how can we see this? Like, what are some concrete ways to show that? Well, on your homework, you had something where it's like, okay, find the inverse of 1, 2, 3, 0, 4, 5, 0, 0, 0, right? So this determinant is obviously 0 because if you take the diagonal, this is an upper triangular matrix, the product 0, so the determinant is 0. So what happens, well, when you try to do the row reduction method in finding your determinant, what do we need on the left-hand side? Yeah, we need an identity matrix, but can we get that identity matrix? No. And the problem is like right there, right? You can't get a 1 there. So that's one way you can see it, all right? So if the determinant of the matrix is 0, you can't get the identity matrix. Another way you can see it is by using the 2 by 2 inverse example. right? So in class, if A was A, B, C, D, right, you showed in class, in lecture, that A inverse would be 1 over AD minus BC times D negative B negative CA. Right? Does that should look familiar? Right, so that's the 2 by 2 inverse trick. Well, what is AD minus BC? Yeah, just the determinant of the 2 by 2 matrix, right? AD minus BC. So this is really determinant of A, right? So this is really 1 over det A times D negative B negative CA for a 2 by 2 matrix. So again, if determinant of A is 0, your inverse is undefined because you have 1 over 0, so you can't calculate it. And so if the determinant of A is non-zero, you can find what that is, and then so you have an inverse. All right, so these are 2 ways to see why determinant has to be non-zero. Okay. Second application. So the determinant also can tell you the number of solutions to a system of equations. All right, so how do you know? Okay, so again, our good friend, AX equals B, comes back. And so there are 2 types of systems. There's the homogeneous system, right, where essentially the right-hand side is 0. Okay, so your B vector is going to be the 0 vector. All right, in this case, if the determinant of A is equal to 0, then there are infinite solutions. Okay, so if the determinant of A is 0, then AX equals 0 has infinite solutions. If the determinant of A is non-zero, then there's only the trivial solution. And what is the trivial solution? It means that X is just the 0 vector, right? So if you think about it, I'm saying AX is equal to 0. Well, obviously, if X is 0, that's going to work, right? So that's why we call that the trivial solution. Okay? So if the determinant of A is non-zero, then only the trivial solution is going to satisfy this. Okay? If you have an inhomogeneous system, right? So B is not the 0 vector, it's something else. This gets a little more hairy in the sense that one of these 2 tells you absolutely nothing. So determinant of A not being 0, right? If the determinant of A is 0, there's either no solution or there's infinite solutions. And this is depending on B. Okay, so for an inhomogeneous system, determinant of A equals 0 doesn't really tell you much. However, if determinant of A is non-zero, then there's one unique solution. All right, and the reason why there's one unique solution is, well, I have AX equals B. Determinant of A not being 0 means I can invert it. So I multiply both sides by the inverse, and you see that X is equal to A inverse times B. Right, and this was shown on your homework, your recitation homework actually for this week. Okay. Any questions? All right, so that's it for determinants, really. I don't think there's too much. Did McGrath cover anything else in lecture about determinants? Because he spent all day yesterday talking about this, right? Yeah, so that's all I have for determinants. So if we don't have any questions, okay, let's open up then the can of worms that are vector spaces. So vector spaces, all right. So first thing I want you to do is forget what a vector is. All right, just whatever, just wherever you thought your notion of vectors, that's not what it is. All right, so this guy, no. All right. Let's give the definition of a vector space. And we'll see why vectors aren't considered like. So when you have a vector space, essentially like a matrix can be a vector as well. So the name vector space is almost kind of like misleading because you think only vectors can be inside, but really matrices form a vector space, polynomials form a vector space, differential equations form a vector space, right? So they're not just vectors. Let's give the definition of a vector space. A vector space is a non-empty set of elements defined with an addition operation denoted as plus a scalar multiplication or scalar can't write operation, which is called times or dot. That's what scalar multiplication is. So you have these two operations, and where the scalars are from a field called F. And so we usually refer to this field. This is usually R, which are the real numbers, or C, which are the complex numbers. Okay? And 5. This set needs to satisfy 10 axioms. And oh boy, I don't think I remember all 10. There's 2 of them that are really important. So the first one is closure under addition, closure under scalar mult, closure under addition, scalar multiplication. There's, I think, associativity of addition. Commutativity of addition. What else? Left distributivity of scalar mult. Right distributivity of a scalar mult. existence of an additive inverse let's see, existence of a zero vector, so it's called additive identity, commutativity, wait, no, that's not, associativity, sorry. Associativity of scalar mult. Oh boy, I'm missing one. I think it's scalar mult identity. I think this is all of them. There's a table in your book that has all of them. This is off the top of my head. But the only ones that we really care about are these first two. All right. And that's because if we show that a set is closed under addition and closed under scalar multiplication, that's usually enough to deduce that this is a vector space. So a lot of this stuff on the screen right now might sound like absolute garbage. Like, what is all of this? Don't worry about it. Once you see more of it, it'll make more sense. But let's talk about the first two: closure under addition and closure under scalar multiplication. So let's take a set which is the set of 2 by 2 real matrices. And it's called M2R. Okay, so essentially, you just take a 2 by 2 matrix, and it's A, B, C, D. All right, and we want to show that this set is a vector space. Okay, and so how do we do that? Well, closed under addition. All right. So we want to see if A plus B, all right, if A is a matrix and B is a matrix, we want to see if this matrix is inside our original set, M2R, right? Given that A and B are inside M2R. So we pick two arbitrary matrices in M2R, call them A and B, and we want to see if that's true or not. Okay? And the idea is the following. What do two matrices, just give me two arbitrary matrices, 2 by 2 matrices.
The identity nature.
Okay, a lot more general than that. Give me two arbitrary general matrices.
A, B, C, D.
Okay. We need another one.
E, F, G, H.
Okay, that works. Right? So, are we convinced that this is a 2 by 2 matrix of real numbers? Any objections? All right, so that's a 2 by 2 matrix of real numbers. Okay, we're all good. Is this EFGH, is that a 2 by 2 matrix of real numbers? Yeah, all right. So now we add them. A plus E, B plus F, C plus G, D plus H. All right, so first of all, okay, so this first matrix, A, B, C, D, we say this is N M2R, right? It's an element of M2R. Remember, M2R is a set of matrices. Set of all 2 by 2 matrices is M2R, right? So this guy is in M2R. This guy is in M2R. All right, the real question is this matrix in M2R? It is, right? Because what's the definition of M2R? 2 by 2 matrices that have real numbers inside of them, right? Well, is A plus E a real number? Yeah. Is B plus F a real number? Yeah. Right? So yeah, this thing is a matrix of a 2 by 2 matrix of real numbers. So in that case, yeah. So this is a matrix in M2R. So what we've shown is that for any two arbitrary matrices that we choose, their sum is also going to be a 2 by 2 matrix with real numbers inside. Okay? So we've shown closure under addition. Closure under scalar multiplication. All right. So we'll assume that, so what we want to do here is that if we know A, so if we take a matrix A and it's in M2R, right? So A is a 2 by 2 real matrix. We want to see if K times A is in M2R. All right, so we take some scalar K and we multiply our matrix A by that scalar, and we want to see if that result is also a 2 by 2 real matrix. Let's say K is in R, so we're talking about real vector spaces. Right, because if you remember from before, I said that your field could be real or complex, right? So up here, it's R or C. So here, we're almost always we're going to say that we have a real vector space. And so if we say we have a real vector space, then our scalars come from R. All right? So if I take my arbitrary matrix A, B, C, D, right, and we're convinced that this is inside M2R, all right, and then we take our scalar K, which is a real number, what do we get? We get Ka, Kb, Kc, Kd, right? Is this a real matrix? Is this a matrix of 2 by 2 real numbers? Yeah, it is, right? Because K is a real number, A, B, C, D are real numbers, and so if you multiply them together, that's a real number. So yeah, this is also in M2R. So that means that Ka is inside M2R. So this is closed under scalar multiplication. Okay. That's about as much I'm going to show, because everything else is like, is A, so if I have two matrices, A plus B, is that the same as the matrix B plus A? And yeah, they are, right? So yeah, so the matrices, they're a vector space, right? And that's why you don't want to be fixated on the idea of vector spaces only deal with vectors, because, well, matrices are vectors too. Okay? So you guys will formally begin vector spaces tomorrow. Next week, we'll probably talk about subspaces and more of the vector space theory kind of stuff. So, all right, let me hand out homeworks for next week. If you haven't turned it in already, do so up front. Okay, a few announcements that I was going to announce. So I actually have some good news. So there was some miscommunication between, I guess, Professor McGrath and the TAs. So we thought that there was only going to be 2 drops this semester, but it actually turns out there's 2 drops for homework and 2 drops for recitation homework, so you have 4 drops. So that's the good news. So instead of just having 2 drops, you actually have 4 drops. And then, yeah, I guess recitation homework, We're gonna try to tone them down. So if you look at next week's like homework assignment, it's gonna be substantially easier than the first two. And the idea, like, and a lot of people have been asking, like, are we supposed to know everything in the first two? Like, for example, there's that one energy problem from homework 2 where everyone's just like, what is this? It's some physics thing. It was just meant to be as like an application of like, here's where you see differential equations and stuff like that. Like, a lot of people had problems with it, so it's fine if you thought the stuff was a little hard at the beginning. We're actually going pretty quickly through this class relative to last semester. So the pace will slow down once we get to vector spaces. So in a sense, the class will get easier as the semester progresses. Okay, so office hours, I have them on the board. They're also listed on my website. This recitation is recorded. It'll go up on my website on Friday. I still have the Friday sessions this week, so the sign-up will start sometime in the afternoon. The link will be posted on my website as well. So in the Friday section, we'll probably just do a bunch of like proof type examples.
I want to ask, are we going to get our like homework?
Oh yeah, if you want homework, pick it up during office hours, because I have a huge stack. No, there's no cheat sheet for
like either section.
I think there's none for either section. So.
Should I go to my previous TA or my
Yeah, if you turn it into yeah. If you just do you switch sections or just TAs? Okay, then yeah, then whoever your TA was before.